An autonomous system, or AS, is a set of routers under the same control and running the same routing protocol. Inter-AS routing is between one AS to another AS. This type of routing uses the Border Gateway Protocol, or BGP. Intra-AS routing is routing within the AS, and this type of routing uses Interior Gateway Protocols, or IGPs. Intra-AS routing has two protocols: Open Shortest Path First, or OSPF, and the Routing Information Protocol, or RIP. Routing Information Protocol is a protocol that uses the distance vector routing algorithm. In this example, I will walk you through and demonstrate how distance vector routing works. Distance vector routing uses the Bellman-Ford equation to calculate the least cost path between nodes. The distance vector routing algorithm is iterative, asynchronous, and distributed. It is distributed in that each node receives information from its directly attached neighbors, calculates the minimum distance using the Bellman-Ford equation, and then distributes the results of its calculations back to its neighbors. It's asynchronous because it does not require all of the nodes to operate in lockstep with each other. And it is iterative because the process occurs in iterations until no more information is exchanged between neighbors. Because of this, the distance vector routing algorithm is also self-terminating. This network topology only has 3 nodes. Each node initially only knows a distance of itself, which is 0. During the first iteration, every node sends its vectors to every other adjacent node. Every node then updates its routing table according to the Bellman-Ford equation. Each node calculates the direct path between all of its adjacent nodes. During the first iteration, every node sends its vectors to every other adjacent node. Every node then updates its routing table according to the Bellman-Ford equation. Using the Bellman-Ford equation, the distances will be computed as a minimum of the sums of all distances to every other node through any intermediate node. Now, what does that actually mean? Well, A's routing table receives B's distance vector. A knows the cost between A and B is 10, and now knows the distance between B and C is 5. Therefore, it can update its shortest path to C in its routing table, which is no longer 25, but now 15. Now, A will receive C's distance vector as well. But after using the Bellman-Ford equation, it too will update its value to 15. Just as A's routing table was updated, B and C's routing table will also be updated with every other adjacent node's distance vector. Now, what happens when the cost from node A to node B changes from 10 to 50? Node B can no longer get to A with 10. Node B can get to C with a cost of 5. And node B thinks C can get to A with a cost of 15. So instead of 10, B thinks it can get to A with a cost of 20. Node B will now send its new distance vector to node C, which is 20, 0, and 5. Now node C will update its routing table. Node C knows it can get to node B with a cost of 5. And node C thinks B can get to node A with a cost of 20. Therefore, C thinks it can get to A with a cost of 25. Node C will then send its distance vector of 25, 5, and 0 to node B and continue the process of counting up. The next iteration, C will realize that it has a direct path of 25, which is a new low-cost path directly to A. This problem is called the counting up or count to infinity problem. The solution to this problem is called the Poisson reverse. The way the Poisson reverse works is when B has to route through C to get to A, it will send its new cost to A as infinity. When node C receives B's new distance vector with infinity, this will prevent node C from going back through node B and immediately take the direct path to A with cost of 25. Does the Poisson reverse solve the general count to infinity problem? It actually doesn't. Loops involving 3 or more nodes, rather than simply 2 immediately neighboring nodes, would not be detected by the Poisson reverse technique. Let's conclude by restating some of the distance vector attributes. In terms of message complexity, the distance vector algorithm requires message exchanges between directly connected neighbors at each iteration. We have seen that the time needed for the algorithm to converge can depend on many factors. When links costs change, the distance vector algorithm will propagate the results of the changed link cost only if the new link cost results in a changed least cost path for one of the nodes attached to that link. How fast is the convergence of distance vector? The algorithm can converge slowly. It can have routing loops while the algorithm is converging. Distance vector also suffers from the count to infinity problem. And last but not least, robustness. How robust is distance vector routing? If a router happens to fail, misbehaves, or is sabotaged in some way, under distance vector, a node can advertise incorrect least cost paths to any or all destinations. More generally, we note that at each iteration, a node's calculation in distance vector is passed on to its neighbor and then indirectly to its neighbor's neighbor onto the next iteration. In this sense, an incorrect node calculation can be diffused through the entire network under distance vector.